today we'll be talking about the Thermo Fisher Spectra Ultra that was installed here at CCEM. Click. Oh, I know I have to do this. Okay. So, as Sam said, we're here today to discuss the replacement of our beloved Titan High base, which was installed in 2009. And then just last year we removed it, and the new instrument that was installed was the Spectra Ultra TEM. And so if any of you have worked with the Titan High base, you'll notice that we have the same enclosure here. It's just the guts are different. And then maybe the sticker on top, right? So it was signed off on our very last day before Christmas holiday last year, so around this time. So really it wasn't available for use until January of this year. So I just put 2023 right here. And I just like to note that I know that this webinar says Thermo Fisher Spectra Ultra, but I'll be specifically talking about the Spectra Ultra here at TCM. So like with many instruments, each one is slightly customized. For example, the Electron gun. Some can come with an XFEG, others with a cold FEG, a CFEG. The other option is, for example, the type of monochromator that you can equip your TM with, the type of EDS detector, and also, you know, the type of EOS spectrometer that you're going to put on it or even not put on it. So here at CCM, this is the list of things that we have on our Spectra Ultra. And also just for reference and reminder is the things that we also had in our Titan High base, just for comparison. So here we also have an XFEG. And then, so now we have 4 different KVs instead of 3. The 4s are 30, 60, 200, and 300 kV. And then we also have a monochromator. Here on the Spectra Ultra, we have kind of like an upgraded version. It's called the OptiMono. Actually, we actually have the OptiMono on the Titan for a little bit, maybe about a year. But that's okay. So we have the OptiMono here on the Spectra, and then also just I would say normal monochromator, or the normal Thermo Fisher monochromator as well. We also, again, have the probe and image corrector. This time with the Spectra Ultra, it can correct up to the 5th order aberrations. So we'll talk more about that in a little bit. And then the pole piece is a little bit different. So now it is 5.4 millimeters, and that's mainly to accommodate our Utra-X EDS detector. And you'll see in a little bit, like this EDS detector is just very nice. Much, much better than what we had on the Titan High base. Okay, and then we also have our, normal ADF STEM detector. So we have a HOTF detector, and then now it's equipped with the Panther STEM detectors. So these are segmented detectors that allows us to easily acquire images for different STEM imaging techniques. And we'll talk more about that later as well. We can also do tomography, which is normal, but now we can do it tomography with EDS. We have, of course, an EOS spectrometer. This one is the Gatan ContinuumK3. So this is the newest generation of EOS spectrometer produced by Gatan. The other one on our Titan High base, we had the ContinuumK2. So they both have direct electron detectors. It's just that now we just have a newer generation. And then, of course, we can do 4D STEM using our Ceta-S, or fast Ceta-S detector. We could also do 4D STEM with the Gatan ContinuumK2. on the Titan, but this time it is done so through Velox instead of Gatan. And then last but very not least, we have OptiSTEM, OptiMono. So these are our automated functions that I'll talk more about in a bit. And I just like to make a note here that our Gatan Quantum K2 GIF, it is still around. So it was removed off of our Titan high base and moved on to our Titan low base. So our low base is now, it's a single aberration corrected TEM. It's can still do STEM, and it's just not a probe corrected STEM probe. And we can do EOs on it with the K2 direct electron detector. So it's still around, and this is still a really great microscope. So if you didn't know, we do have EOs on the Titan low base now. So, and the software is upgraded, so you should be able to hop on it easily and use it. Okay. If you have any questions about that, just, reach out to me or Carmen. Okay, so before we start, I kind of also wanted to just show some fun pictures of the deinstall and the install of the Spectra. I mean, it's not every day that you get to see, one of these go and one of these come in. So I thought it might be a little fun to start off with that. So this was last summer, and here, let's see, my pointer. Here, this is like kind of our dining area, and this is where we have our Titan high base ready on its way out through the door. And then here in this picture, it's being craned out. So the only way to kind of take it out was to crane it out of our through this area, which is like kind of like a courtyard area. And then on that very same day, we actually had our Spectra Ultra come in. So it was craned in, wheeled in into the enclosure here. And now you can see all the panels are off for the install. And yeah, it was kind of crazy, kind of fun. A big shout out to, the SFR engineers for handling all of this and making it possible. It was a lot of spaghetti and a lot of, I don't know, chaos, but I'm really glad that it all came together and without any major hiccups. So really a big thank you to them, especially Jesse, for making this happen. And so now we have our nice Spectra Ultra in our old, still very good enclosure. Okay, so back to it. So I showed you a list of what defines our Spectra Ultra. But if we were to summarize the main differences between this and the Titan high base, I would summarize it in generally 2 points. So the first option is the option to always work at optimized conditions. And so I'll explain a little bit more about that in detail in a bit, but that's basically due to the thermal Fisher constant power lens across all the KVs. And this, what this does is that it allows us to switch KVs and have a stable usable beam in a matter of minutes. It is truly minutes and really great to work with. This means that we can switch from doing, for example, monochremated work at 60 kV and then switch over to high resolution STEM imaging at 300 kV all within the same day. Additionally, it's also equipped with these automated softwares now, which are really cool. So we have the AutoSCORR, which is controls the automated kind of alignment for the correctors, the probe corrector. And then we also have these OptiSTEM and OptiMono softwares through Sherpa, which allows us to do low order aberration correction directly on our sample. So that's this OptiSTEM. And then we also have OptiMono, which also does the automated alignments for monochromated work, whether you're doing just regular monochromated work or multi-monochromated work. It automates it from start to finish. It's pretty amazing. Okay, and so the second thing here, major difference, I would say, is the fast acquisition, and that's due to the hardware and the software. So here, as I said, on the Spectra Ultra, we have the Utra-X EDS. We have our Panther STEM detectors. We have our Gatan ContinuumK3, our fast Ceta-S, and then, our software, our Velox software, which is actually a nice improvement, in my opinion, or a nice upgrade to the it's blanking in my head right now what it was, but the old acquisition, TIA, the old acquisition software. Okay, so let's see. So yes, fast acquisition. And so what I mean by fast acquisition with the EDS, I mean we can really acquire a fast EDS, like an atomic map, in just 10 minutes. This was done on our Spectra Ultra, but this is not an uncommon thing. It seems that this Utra-X EDS system really can produce results, and it's reproducible. So it's really great. So in this talk, what do we mainly mean by like advancing the microscope, advancing, your TEM analysis, is that what we're saying is that it allows us to optimize the data acquisition conditions and minimize the time spent acquiring data. And thus, it really allows you to collect more data if you wanted to. Okay, so first, let's talk a little bit more about this first summary here, which I think is really great, which is the constant power lens. Okay, so why would you want to work at these optimized conditions? Well, it depends on the technique that you're going to do, or that you would like to do on the TEM. So here, as I said, on the Spectra Ultra, we have 4 kVs. So we have 30, 60, 200, and 300. And so these, I would say, are lower kVs, like lower acceleration voltages. And then these are kind of like a high acceleration voltage. So this is kind of like the highest, 300. Now there are many techniques out there, and many reasons why you'd want to work at, a certain acceleration voltage. I'm just listing a few here and the optimal voltages to work at. So first is the high energy resolution or high spatial resolution imaging, so the HR-STEM and the HRTM. Ideally, yes, you would want to work at the highest kV, so 300 kV, which is why? So it's because at this kV, you have the minimal amount of chromatic aberration, and you have more spherical aberration. But luckily, we have our spherical aberration corrector that will take care of that. So when you work at 300, you basically work at minimal spherical and chromatic aberrations, and that gives you really good spatial resolution. The second is EDS. So it's kind of recommended that you work at, kind of like a medium range acceleration voltage, so we'll say 200 kV. And that's because, the ionization cross-section increases, meaning you'll generate more signal with decreasing acceleration voltages. And then here, the third is EELs. So here it says EELs, we have it falling into 2 categories. So we have core loss and low loss EELs. So for the core loss, this is your general, like, the generating the elemental maps, right? And so this is the most common application of EELs here in our facility. It would be optimal to work at 300 kV to reduce pleural scattering and take advantage of the high dynamic range performance of the K3 or our directional electron detector, provided by Gatan or produced by Gatan. Okay. And then the second one would be the low loss EELs. And so here you'd use the CMOS detector. And so at low loss EELs, you're probing things like phonon and plasmon excitations and band gap energies, and of course with the use of monochromator. And so it's optimal to work at these lower kVs, in conjunction with the monochromator to increase your energy resolution of your source and reduce chromatic aberrations. And then last but not least, of course, you might want to consider the type of damage that your sample will encounter, and what kV can your sample survive under, right? So we have knock-on damage. So if you have your sample is highly susceptible to knock-on damage, you would want to work at these lower kVs. And if your sample is susceptible to radiolysis, ideally you want to work at the higher kVs. Okay, so this is a few examples, but obviously, the TEM is very useful. It can be changed for a lot of different things, the acceleration voltage. So a lot of times, what we experience is that, say, we pop our sample into the TEM, we want to do high resolution imaging at 300 kV, and then we say, oh, you see it rapidly degrading and disappearing right in front of your eyes. And it's like, well, I cannot work at this kV. I need to switch it. I need to lower the kV to maybe 60. I could try 60 kV. But, so that's what you would the thought process that you kind of go through. And then, so something else could be, say you're working at, you're doing monochromated work, as I said, example before, you're doing monochromated work, and then now you want to switch to high resolution imaging to examine the crystal, the quality of your crystal, say. So you need to switch to 300 kV. And so all of these, examples are commonly, I'm sure many of you have had some thoughts or similar thoughts along these lines. And so in the, I would say, olden days, I guess, you had to change your kV, and that with that, it requires a stabilization time. So normally when you switch to kV, there's a required waiting time for the optics to stabilize due to thermal drift encountered when changing the strength of your round lens. So normally the waiting time was about 5 hours, with our Titan high base, which often meant just overnight, because basically by the time you come to want to change your kV, it's already maybe mid-afternoon, and you do not want to wait around just for your beam to stabilize. So you just change it and then come back the next day and continue your work. Okay, so now with the Spectra Ultra, with this constant power lens across all acceleration voltages, the time spent waiting for the optics to stabilize has dramatically reduced from hours to a matter of minutes. And I know there are many, many great TMs out there, very specialized for certain things, but with this one, I would say this is the main highlight of this microscope. This constant power lens. So now, our waiting time changed from overnight to 5 minutes. So this really allows us to work at different KVs in one session / one day with no thermal drift. Okay, here in this graph, is from the Thermo Fisher site. They show that the sample drift over time. And so what that means is basically your optics, right, is stabilizing over time. And their spec is, oh gosh, this is 5 nanometers per minute. Okay, so that's their spec. And you'll see that within, less than 5 minutes, they reach their spec of changing their kV from 60 to 30. But so that's 5 minutes, and then if you just basically wait another 5 minutes, you basically reach a threshold. So it's pretty stable after about 10 minutes, I would say, and you have a usable beam for high resolution imaging work, no problem. So I just want to, kind of describe a little bit more about this constant power lens. So when you switch your kV, you're normally altering the power required for your lenses to work at that certain acceleration voltage. So, and changing the power of a lens induces thermal drift, as I said. And so the main idea of the constant power lens as the name suggests, is to have the same amount of power going to a given lens. So this is done by having two conjugate coils. So you have basically one round lens has two coils, and they're wound in opposite directions, and they're interleaved like a book here. And so the total magnetic field generated is described by the sum of the currents from these two coils. And the power, so that's a magnetic field, right? The sum of the current coming from these two coils. And the power is described as a square, the sum of the square of these currents. And so they can work together with one another. And so you can change the magnetic field of your lenses and have the same constant power. Now, just to know that they did have constant power lens technology in the Titan high base, but this was confined to a certain acceleration voltage. It was previously, allowed you to change modes, so work at different magnifications, changing the different optics in your microscope at that kV. But now with the Spectra Ultra, that has expanded across all the kVs. So now you can switch your modes within the same kV and also switch your kVs and switch the modes and have a constant beam, which is really nice. Okay, so now in addition, so once you have done your kV switch, you of course need to align the beam. And align the correctors, especially when wanting to do high resolution work. So one of the new thing over the Titan high base, of course, is that we have a better spherical aberration corrector, so the S-CORR corrector, but also we have software to automate these corrector alignments, which is really nice. Additionally, we have Sherpa, as I said, which is the OptiSTEM and OptiMono, to help you automate functions once you do have a workable microscope. So we'll be talking a little bit more about that in a second. Okay, so for the correctors, okay, so we do have a very nice corrector that now corrects up to the 5th order. With the Titan high base, it was up to the 3rd order. Specifically, the spherical 5th order spherical aberration and the 6-fold astigmatism A5 is corrected in the factory, so that is stable for the life of the microscope. It can be tuned a little bit during by the service engineers, but this is something that we do not have to worry about currently. It is going to be stable right now and for the near future. And so with these correctors, we can also reach sub-angstrom resolution for 3 of our kVs, so 300, 260 kV. And like I said, we can automate corrector alignments with the AutoSCORR. And this really allows us to it really takes over the iterative process of tuning the correctors. If any of you, I'm sure many of you have used it, and you're manually just clicking the same buttons, doing a little bit of thinking, but you're just basically button mashing until you have a really nice beam. Okay, and so here is, your standard image corrector. Oh, sorry, not will be the probe corrector, but CS corrector, I would say. Assembly. We also have a nice aberration corrector, image corrector webinar that you can check out. And so with that, here with this S-CORR corrector, here are the confidence levels they give that you can reach with this corrector. So all the way up to the 4th order values. And then, I also put here on the side of how long these are generally stable for. So of course, your 1st order A1 and C1, your deep focus and your 1st order stigmation is, stable on the order of minutes, which is, normal. You have your 2nd order coma, second order aberration, so your coma, and your 2nd order astigmatism. that's stable in the matter of hours. And then, of course, our C3, most importantly, is stable on the order of days. And so this is just to show that, you know, if the corrector was aligned at a certain kV the day before, you do not have to realign them again. You can just correct these lower order aberrations using OptiSTEM, and then these will be fine. So you don't have to necessarily waste time, although it is really fast to do it, to run it again. So just a comment. Okay. And then let's see. Oh, keep forgetting. All right. So just as also another blurb here is that in the actual probe corrector GUI, you can kind of simulate what's the best conditions, your microscope setup should be for the best conditions that you're trying to reach. So for example, here, I know it's really small, but you can put in your convergence angle, you can put in your probe current, and it'll spit out, you know, your D50 value, and also the full width half max of your probe. And so this really allows you to tune, like say if you want to do high resolution eels, you need a little bit higher current, but a higher current that's needed as compared to with STEM imaging. But you don't want to sacrifice, or you want to minimize, right, the sacrifice of the small probe size. So you can just play around with those things over there and kind of help you plan your next experiment. Just something to add there. Okay, so with the S-CORR spherical aberration probe corrector, I just want to show here our spec results. This is pulled from our Spectra Ultra for the 4 kVs and the resolution that we're able to achieve. So here we have our high acceleration voltages at the top, and then our lower acceleration voltages at the bottom. And so here at 300 kV, the sample is gallium nitride, and then this showed that we can reach 0.48 angstroms with a 34 picoamp beam. And then, so gallium nitride is the only one that has, these spots down in this range. All the rest were acquired with silicon. So for the 200, we have 0.69 angstroms with 35 picoamp beam. For the 60 kV, we have a 0.96 angstrom. So that's what we say, these 3 are sub-angstrom resolution beams. And then we have 30 kV, which had a resolution of 1.25 angstroms with a 40 picoamp probe current. Now I have an asterisk here next to the low acceleration voltages, and that's just because I just want to point out that we do need to excite the micrometer to do this high resolution imaging work. So we do that just to remove a little bit of the chromatic aberrations seen at these low acceleration voltages, and so that really allows us to reach higher spatial resolutions. But of course, just to know, at the 300 and 200 kV, you do not have to use the micrometer. Spherical aberrations take over at these high kVs, so you can just work with the aberration corrector then. Okay, and then, as I said, OptiMono and OptiSTEM. So for this OptiSTEM, it's really, really great to use. This is new, and I'm really excited to use it. It's also very, I don't know, I just love it. Okay, so we have the option. It's really small, but here you can just click a button and it will autofocus and auto-estimate for you directly onto your sample. You also have the option here, which is a button for the second order aberration aberration corrections. And so you can just click this button, it measures and corrects, iterates through the process, corrects these aberrations for you. You can choose to do B2 and A2 together or do them separately. is quite fast. So the C1A1 takes about a minute. So I would say, if you're pretty fast, it's about the same amount of time as, or actually, I don't know, yeah, if you're pretty fast, you can, kind of work at that same pace for fixing your focus and stigmation. But for your A2, B2, it takes about 4 minutes to correct, and I think that's pretty fast. And it's really difficult for me to see second order aberrations in the bronchogram. So it's really nice to let the software take that over for you. Okay, and then so here is just an example pulled from the I guess brochure for the OptiSTEM. And so this is before OptiSTEM and after OptiSTEM. So clearly you can see the image was optimized. It fixed first order and second order aberrations, and it was done directly on the sample. So here you have this periodic crystalline sample. It had no issues at all, and it worked just fine. And so that is like one thing that you have to think about, is that this does work for crystalline samples, but if you have a sample that is very like you're working with the powder, so there's a lot of topology in it, so within one frame you have different values of defocus, it is going to have a little bit of trouble finding the right focus if you have different focus values within that same frame. Just something to think about. Also, you need to have good contrast in your image. So say if you just have a whole frame of just amorphous carbon for whatever reason, and you're trying to focus on that, it will fail because it has no features in your FFT to kind of focus on. Okay, and so as I said, we have our OptiMono. So this is just showing our buttons. Like basically it's very simple. You just click a button, you can have it say, turn on my OptiMono, do all my presets, and then tune all. So that means tuning all my stigmators, tuning my focus. It even aligns the slit for you, which is really awesome, and your C2. So and it really does work. Yeah, it's pretty nice, especially when you're tuning the mono stigmators. You can spend a lot of time trying to do that, and if you trust the computer or the software, you can just let it do it for you. I think it's pretty good. Okay, so here's kind of like a workflow uh, that you kind of go through when changing your KV during the session. So first, you'll change your KV, you'll load the alignment file, you'll load the FEG register, you'll perform your rough column alignments, run the auto correction, then you'll find your region of interest. You can run OptiSTEM to fix your focus and stigmation, and then acquire your data. So acquire your nice STEM image, and then repeat the process again. So you'll see here, it's really just a few manual steps. You let the corrector take over, and then you can continue your work of your new KV. Okay, 11:37. Okay, so here I have a quick video, 5 minutes, just to kind of demonstrate truly, if any of you are having any doubts, switching from 60 kV to 300 kV and reaching that high resolution probe in a matter of minutes. Oh, then I need to switch to this and click play. Okay, so here we're going to switch. So the real time, or not the real time, but the time in this video is 10:39, so time 0. And then we're switching the kV from 60 to 300. Okay, and then I speed it up a little because this is just not really the important stuff. But you can load your alignment file here. And the kV is still, you see the high tension is still going up. And then you can load your FEG register. Always load your FEG register after loading your alignment file. We encountered a quick error, so I just had to restart Velox. Okay. And then the next thing that you're going to do is find your beam and then perform your rough column alignments. So here our sample is the gold cross grading, but note if your sample has good contrast in it, or for example, you're working with a nice fib lamella, you can do this directly onto your sample as well. It's a little bit more difficult when you have a powder sample, as I kind of described earlier. Okay, so here we're just kind of centering our beam. Then we readjust our Z height, normalize, and then we set up our imaging conditions to run. Oh, no, actually, I'm checking for coma, just doing some rough coma corrections. So it's a little bit better using the Marquegram. And then we can start the AutoSCORR. So that's 7 minutes now. It's been 7 minutes since I changed the KV. I can start the AutoSCORR. So this is where it will align the correctors and optimize the higher order aberrations for me. And so now I can just sit here. This is where I usually just load my sample into the holder, maybe do some plasma cleaning. It takes about 5 minutes to do. So, or it's also just good to watch it, make sure that your conditions are correct. Normally, if you just see a nice round FFT, then you can kind of assume that your beam will converge and will work properly. If you see some funky things like an oval or lots of stretching or not a clear, maybe even no FFT, then something's a little funky and you can just check it out. Okay, so now that's done. And then now let's say I can go to find my ROI, zoom in. I'm just going to choose this area right here. And then I can bring in my OptiSTEM. I'm sure at some point. Is it going? Okay, yeah. Bring in your OptiSTEM, perform C1A1 to autofocus autostigmate for you. And then you can acquire your image. So it's pretty quick, pretty easy. If you haven't worked with it yet and you used to work with the old correctors, I think you would have a lot of fun using this. So here you can kind of see we can see our nice gold lattice D-spacings there. And I guess I just zoom in a little bit just to demonstrate. It's very nice, very easy. And it's only been, about 11 minutes. Oh, no, sorry, 13 minutes since I changed the KV. So you can truly work at multiple KVs in the same session. Okay. One thing I kind of want to point out is that in addition to, the really awesome hardware, we have this Velox, which is image acquisition software, and it really allows us to acquire nice images. So they have this feature called drift corrected frame integration, or DCFI, in Velox. And this is an acquisition series mode where you can acquire a given set number of images. And then after this, you have 2 clicks, and then you have this final image here. And so what this does is it takes 10 of these. I told it to acquire 10 images. You stack them together, correct for drift, and then stacks them together to produce one final image with good signal to noise ratio. And this can be performed with any TEM or STEM image. And it's really, really useful if you have, drift, your image is drifting, or you have beam sensitive material. You can, collect multiple frames at a very low dose and stack them together to produce one image. And you can do this directly in your session, directly after you acquire your image. You don't have to wait to, at the end of your session to go onto a post-processing computer to look at your final image. It can be seen directly into in your session. Okay, so the disadvantage here is that I would say you can't combine separately acquired images and do this function in the software. You have to use a series acquisition. Okay, so that kind of describes the first really awesome thing about this Spectra Ultra. Now with 15 minutes left, we're going to kind of talk about, I'm not going to breeze through it, hopefully not, but the fast acquisition, so the hardware and software that comes with this microscope. So just kind of following along here with the high resolution imaging, we have our Panther STEM detectors. And so what that means, or what makes them really cool, is that they're segmented detectors. And what you can do is that you can explore different types of STEM imaging and STEM image acquisition techniques. So here we have our two. So this is our annular detector and our kind of like bright field detector. They're both segmented to here. So each one has 8 segments. You have 1, 2, 3, 4, and then you have the smaller region, inner region here. Same thing with that one. And so with this, you can have different acquisition techniques. So the first one is that you can use them as a normal annular detector, as if you have an unsegmented detector. And so this is where you basically sum all 4 quadrants to produce an image. And if you choose, appropriate camera length, you can collect ADF, ABF, and BF. So annular dark field, annular bright field, and bright field STEM image. And this can be all at the same time. The second type here is exploiting the segmentation of these detectors, in which we no longer sum these segments together, but instead we use the information collected on each quadrant and individually process them. Okay, so that is why each one is colored different color, I guess you could say. So with this, we can generate DPC images, so differential phase contrast images. And so the idea comes from this. So in the first case here, we have, oh, sorry, my laser pointer. Okay, so in the first case here, we have a STEM probe where, we have this seabed pattern, falls on the segmented detector, and then you can see all 4 segments are seeing equal amount of counts here. Okay, but when we, in the second case here, when we introduce a sample, right? So we have, what is this? We bring a sample, it's made of matter, which has an associated electric potential, and then an electric field is generated with the movement of the beam through the sample. So the transmitted beam is ever so slightly deflected in response to this electric field. And this, kind of follows Gauss's law. And so what we can do is we compare the difference between a pair opposite quadrants. So here, for example, quadrant 2 and quadrant 4 have about the same intensity, while 1 and 3 show a difference where there's more signal collected on quadrant 3 than quadrant 1. And so this really describes the movement of the center of mass of a CBID pattern. And this can be linearly related to the electrical field in the sample. So you can, with this, with this, you can extrapolate different signals based on Gauss's law. But just to summarize, you can get the magnetic and electric fields of your sample using the DPC. You can look at charge density with DDPC, and then you can also look at electrostatic potential with iDPC. And so here in this iDPC, it's really nice because the intensity tracks or is proportional to the intensity, or sorry, the atomic number. So this is where you can collect images of high and low atomic number in the same frame. So let's see. Okay, now with our Panther detectors, we can do all these types of imaging, but here I'm just kind of gonna just show examples of these Panther detectors in conjunction with the probe corrector. So that really gives us really cool results where you can look at elements at the atomic scale, right? So here's a nice example, pretty famous example of a gallium nitride crystal, right? This is a normal HOTF image, and so where the intensity is squared, proportional to the square of the atomic number, right? So here we have gallium, which is very intense, right? We don't see the nitrogen. With iDPC here, we can make out this nice smaller nitrogen atoms with right next to the gallium, and it does correlate with the simulated crystal pattern on the right. And with the aberration corrector, when you use it in conjunction, you can really see that we have, this, what is this? 1.1 angstrom difference between the nitrogen and gallium. So it's when coupled with the aberration corrector, it makes really awesome images. Okay. And then here's another example, right? Is that you have yttrium aluminum garnet crystal. Here's the STEM image, HOTF image here, and then we have a DPC image here, iDPC image here. And so here in this HOTF image, you have this aluminum, the bright dots are basically aluminum and yttrium columns here, as shown in this diagram here. Sorry, it's a little small. But here in between, we have this aluminum only column, and that is difficult to see at this camera length with this detector, HOTF detector here. But now, when we introduce iDPC, we can clearly make that out. What is also kind of cool is that we can also see this kind of halo around this yttrium aluminum column. And that, I believe, is due to it's surrounded by this oxygen kind of column here. And then same thing up here. So now we can make out this aluminum column surrounded by oxygen, and also the oxygen surrounded by the yttrium aluminum column as well. So pretty cool. Now for the setup itself, I just want to make a quick comment. It is pretty simple to do in Velox. This software is really easy. You just kind of click a few buttons. You do need to do a few alignments just to ensure that the quadrants are representative or showing representative differences, of your beam. And then yeah, I would just say that with this, it's very nice images, but you really do need a nice thin sample. So shout out to Bhavesh for making the sample here. This is really nice and really thin, so it really allowed us to see that. But if you do not have a thin sample, it's thin, but it needs to be extremely thin to do this. So something like 70 nanometers doesn't work the greatest. It will still work, but ideally you'd want a really nice thin sample for this technique. Okay, and then next, sorry, 5 minutes. So is EDS, this is the Utra-X EDS. This is the one that is specific to the Spectra Ultra, right? So the Utra-X EDS system. You can have your Panther on other Thermo Fisher TMs, but the Utra-X is the only one that I believe it comes with the Spectra. Like you can get it with the Spectra. Okay, so it is collecting EDS is definitely one of my favorite things on this microscope. So one thing they advertise is that you can really collect good signal to noise ratio data. You need less dose to acquire the same information. So here on the left, we'll just say compare Super X to the Ultra X. So we have, if you do a line profile, this is the same intensity, but showing the same intensity, but it required around 6 times less dose than Super X. And Super X is here on our Talos 200. So it really is really, really sensitive. You can and this helps with preserving your sample during an EDS acquisition. Here's another example where we collect EDS of, nanoparticles just less than 10 nanometers in size. The total time was just 20 seconds, and you can already see this kind of 1 nanometer kind of core of an element here. And then here's another example where we can do EDS, atomic EDS, in conjunction with our spherical aberration corrector to collect a atomic EDS map in a matter of minutes. So this one took 10 minutes on the sample of STO. One other, oh, sorry, this got cut off here. But another thing is that this EDS system works really well with low elements. So low atomic number elements. So for example, this is nitrogen. This is not the main point of this image here, but I just this is nitrogen though, and so you can kind of see, we'll kind of just ignore the dual and the ultra, but you can kind of see like in this bottom right frame here with 100 frames, you can see multiple layers of nitrogen in this EDS map. This is, from their brochure, but it really is truly really nice at collecting low atomic number information. So I think that it can rival with EELs. So it's much faster to set up. I think that we're gonna find it can replace a lot of EELs work in the future. The EELs, of course, is always great. It is very nice to see you can get a lot of information from EELs, but if your sole purpose is just to see elemental mapping and no chemical information, I would say you can get a lot with using EDS in a short amount of time. Okay, sorry. So one last thing is that, of course, one disadvantage here is that we need to use specialized holder with this EDS system. So with our pull piece, you have to use these Utra-X EDS holders. Sorry for the images here. I just grabbed them off the internet. Shout out to SOAS, Hawaii. I used to work there. And then we have an analytical. So this is showing our double tilt analytical holder, and this is our analytical tomography holder. So with these, you can do EDS with them. Unfortunately, with our older, Titan and Talos holders, you cannot use EDS. You cannot acquire EDS with these holders. It will damage the detector. You can use them, but what instead you should use is EELs to collect spectroscopy. So for example, if you want to do cryo or heating experiment, you'll have to use EELs. Okay, and then lastly, but not least, is our, of course, ContinuumK3 GIF. We have similar conditions to our ContinuumK3. I would say, just to summarize, we do have our high resolution package. So that's our 1 millimeter entrance aperture and our really high dispersions. But that cool thing is that we can now, with our K3, we can do dual EOs. So that's really, really nice to use because you can collect your zero loss peak at the same time. Or you can also do, 2 core loss windows. And then another cool thing is that you can do auto alignments. So this button here is ZLP lock, which auto aligns your ZLP during your acquisition. So you no longer have to align your ZLP after your data acquisition. So it's really nice. And so here's just a few examples. And of course we can reach, really high 18, 15 milli-V resolution with this microscope and this GIF system. I'll just skip through this. So just kind of check out the new features. You can find out you have that on digital micrograph, not specific to this microscope, but to just the newer generation of digital micrograph. So it's really cool. Internal standards, it's really great. I encourage you to look more into it. And then of course, we have our Ceta-S PreGIF camera. This can be used for 30 to 300 kV. It is a 4K detector and it's great for HRTM imaging in situ and 4D STEM. It's really fast. It's really sensitive, as you can tell, with just 5 what's that? Electrons per pixel. Then you can get really nice image here, and that's nice to work with beam sensitive materials, or you want to minimize damage. Okay, I'm so sorry for blowing through that last little bit there, but thank you very much for attending. If you have any questions, please put it in the chat, I guess. And I'd like to thank CCM and all of you for joining us here today. So I give it back to you, Sam.
Great, thanks Natalie for the awesome presentation. It made me really jealous that I don't get to use the Spectra.
Oh, you can, no problem. It's pretty easy,
okay,
all automated, so.
Yeah, I know, that's what I was jealous. I remember sitting on the Titan doing the alignment, so the automation is great.
Yeah.
So with that, there's the one question that came up, and if you have any questions, again, please put them in the chat or in the Q&A. So one question is, can we inspect with this polymers and powder materials? And well, you mentioned about the EDS and the TEM, so I'll let you answer that. Maybe they're interested in what you would suggest for KVs and experiment setups.
For polymers and what's the other?
Polymers and powder materials.
Powder materials can vary, depends on what your powder material is. But polymers, no problem. Depends on what kind of polymer that you have. Some are more conductive than others. Depends on what kind of analysis that you're doing. So if you just want imaging done, just to look at the morphology, or if you want, spectroscopy done to confirm, like this is carbon, you want to do, or you can do EOs to look at the bonding, the honest regions of that carbon, to look at the type of carbon. So you can do all of that, of course, with this microscope. You can definitely put soft materials in this microscope, no problem. But I guess you just need to kind of, oh, it's for EDS. Okay, no problem. You can do that. I would probably just do it at 200 kV just to confirm that it's carbon. No problem. Yeah.
Other questions. So for the AutoSCORR, they wrote, no need for sample removal. Could you please elaborate? Do you still need the amorphous region in the sample, or is a crystalline sample also usable?
Okay, so that you would need amorphous region for the S-CORR, the image corrector. But for the probe corrector, you can do it directly on your sample. Like I said, you just need to ensure that you have good contrast in your the image or the region that you're using to correct. So it needs to have good features. And also you need your defocus needs to be stable throughout the frame. So say, for example, you're looking at a powder, and I'm sure if you can kind of imagine, right, you have a powder with, varying heights. You can't control that. If you're at lower magnification, you have a region where you have, a certain region of your frame that's in focus and then another part that's not in focus. And so you cannot do that. The AutoSCORR will not work in that situation. I would say you probably just need to swap out your sample really quick, put in the standard, align on that, and then put your other sample back in. So, yeah, that's what I would say to that.
Looks like there's one more question. Can you do nano beam electron diffraction work with a small C2 aperture, maybe of about 15 micrometers on the microscope? And then they wrote, capturing spot patterns in the STEM mode.
Yes, of course. You can definitely do that. You could do that also with the old Titan as well. So this is no different. You have a variety. I can't remember off the top of my head where it's the smallest C2 size. Is it 20? I'm not sure. It might be 10 or 20. But there's a range of C2 apertures that you can use, definitely. And then with our Ceta-S detector with the high dynamic range, we can definitely acquire that without risk of damaging the detector, especially when you have DCFI. So DCFI, you collect multiple frames, fast exposure times, and then just stack them together to produce a nice diffraction pattern. So yes, it's possible.